Hey everybody, so this is the third lecture on the waves and optics section. Here we're going to talk a little bit more about some of the wave properties of light. For the most part, we haven't really discussed a lot of the wave properties. I kind of briefly said that light was a wave, but it turns out that some of the things that talked about so far, in particular reflection and refraction, technically can be described without considering light as being a wave. Because of this, there was a lot of confusion when we first started trying to discuss what light was, because there were some people who consider it a particle, some people consider it a wave, and there was a whole lot of problems. So we're going to talk a little bit more about what were some of the properties that led people to thinking that light was a wave. Um, in particular, we're going to talk about how it creates what's called interference patterns. Now, a quick heads up, I said before that the first two topics in this waves and optics section were very similar. Dealing with mirrors and dealing with lenses. Uh, I also said that what we're going to talk about today with the interference patterns and what we're going to talk about next time with diffraction patterns, you'll notice that once again they're very similar. So hopefully, if you feel like you're not really completely understanding it 100% at the end of this one, hopefully by the time we get to the second section where we get to the last chapter, uh, you'll feel a little bit more comfortable with the additional kind of refresher. All right, so what ended up happening was, as I said, there were some properties that people were having trouble with of describing as to why is this a wave thing. Like I said, a lot of people weren't aware or understanding why was diffraction something that waves could do. Like, what about waves allowed it to diffract? If you remember, diffraction was when you had a boundary or an obstacle in in the path of a wave, and then the wave would kind of go around it. It would eventually, meet around the object, and there would be like almost that little finite-sized shadow behind whatever the obstacle was. And there are things like, depending on the size of the wavelength, it changed how much it diffracted. So people were wondering, well, why is that occurring? And why is refraction something that waves are experiencing? So one of the things that kind of came up as a way of trying to describe this was something called Huygens principle. Now, what Huygens principle does is it basically gives us a way of determining um, or a way of describing the concept behind some of these phenomena. So, what the statement is that every point along a wave front, which are, if you remember, they're the crests of a wave, like you're looking at a top down view, these are all the waves. Every point along that wave can be considered as tiny sources of little tiny waves themselves that spread out, and when they interfere with all the other waves created, they'll create another wavefront. So, like for example, here you can see there's a crest and essentially a trough, because it's not a crest interacting. That would result in nothing occurring at this section. But over here, where you have a crest and you have a crest over here, that's going to create your next wavefront. So this was what Huygens principle was kind of looking at, was this idea. So um, if we take that, we can actually use that to explain diffraction a bit. That the wave comes in, this obstacle pretty much blocks all the tiny waves over here, but the part that comes over here that passes through here, well, it's going to create a new wave that's going to cause it to spread out and kind of almost bend outwards over here. And that would also kind of explain why the wave seems to spread out more or less based off of the size of the opening versus the wavelength. So um, the Huygens principle is a way of kind of explaining conceptually of what's going on. The ray model that we kind of use, it doesn't really take that into account. The ray model actually pretty much takes the concept of wave and tries to explain it as if it was a particle. So that's why um, the ray model doesn't really work in this case, which is why they had to come up with this. So if you're a little confused, don't worry too much, because this is just really the concept behind it. Um, but it was really meant for laying down the foundation of, differentiating what is a wave and what is a particle, and how can we differentiate them. Um, so uh, now, like I said, we can kind of use this idea in order to explain diffraction, or sorry, refraction as well. So, for example, we have the wave coming in and bending. It makes a lot more sense when we incorporate um, Huygens principle into this, because now what we're going to see is, we have the waves. The waves in here are going to now travel a lot slower, so they're not going to their wavefront is not going to go nearly as far as the ones out here. So um, when they come in, yeah, they're not going to go as far. While over here they do go much further. And if we still use the ray as representing almost like a normal vector, normal to the path, we actually will see that it will end up bending based off of the waves traveling slower in here versus out here. So again, we could just use the idea of Huygens principle for this, and this will also lead us into coming up with Snell's law by using a little bit of trig functions here. All right, so it does kind of make sense. One thing to note is that we're going to discuss this a little bit later, but it is extremely important that you know that when a wave is traveling into a new medium, its velocity will change. Uh, and as we know, velocity is based off of, is the product of frequency and wavelength. Well, if the velocity changes, then one of those two terms has to also change. It turns out that it's the wavelength that is changing. The frequency will never ever change. It's why when a person jumps into a pool with a red shirt, they still have a red shirt. When you're looking at them while they're in the water, you don't automatically think that they have a new color shirt on. The color is still red based off of the fact that that's the frequency not changing. So definitely something that you kind of want to remember, that frequency never changes. Things like wavelength and velocity will. Now, this also does kind of explain a little bit about mirages and optical illusions. So I put in here that it needs to be a hot day. However, it actually turns out it doesn't necessarily need to be hot. What it needs to be is sunny. And it needs to have been sunny for a while. But if you have a day where the sun's been out for a while and has been beaming down on a blacktop road, like a highway road, what's going to end up happening is the air right above the surface of the road will actually end up becoming extremely hot. Now, it turns out hot air, as you know, is less dense than cold air. So what we end up getting is the refraction of the air near the bottom is going to be a lot different than the air outside. So the way this ends up kind of working out is that the light that is traveling, that is going down here, will actually end up bending due to Snell's law, and will end up actually reaching the observer instead of just hitting into the ground like it would normally do. And as I said before, because of the way our eyes perceive light, will consider this light beam as if it was coming from a straight line inside the concrete. So this is just a good picture of what it looks like. It almost looks like the cars are driving on a watery surface. I do recommend that when you're driving to try to keep an eye out for this. Like I said, it's got to be a day where the sun's been out for a while. I did test this, and it does work in the winter time, as long as you have a very clear day and a very sunny day. All right. So yeah, continuing on, we're going to talk a little bit about interference and kind of what light ends up doing. So we're going to talk about what's called Young's double slit experiment. Now, Young came up with this experiment in order to actually determine once and for all, is light a wave or is it a particle? Now, if you have two slits and you're sending particles through those two slits, what you expect is two slits, two beams of collisions occurring on the other side. Imagine you had two openings in a wall and you're throwing balls randomly through that. They're going to hit the other side and they're going to create two beams of light, something like or something like this. You have your this is going to be the two openings that you have. This is just going to be some sort of collision. When you send beams in, particles, they'll always end up hitting and creating these beams of straight lines that come in like this. Ignore my mess. But any particle that comes in over here is just going to be blocked. So the thing that you view are just these lines on the other side. Now, on the flip side, if it was a wave, what's going to end up happening is that you'll end up creating multiple lines on the other side, because because of Huygens principle and because of the concept of diffraction, as the wave goes through those openings, it will now become new wave sources that will end up going outwards in a curved path. And as they curve, they'll end up interacting with each other at some point, creating these areas of constructive interference and destructive interference. Well, it turns out that light ended up creating these patterns. So here's what we end up having. If it was a particle, we would have gotten something like this, two shadows. But what we ended up actually seeing was this, multiple lines. So this led him to believe that light ended up being a wave instead of a particle. Now, it turns out that even this is wrong. It seems that light in itself is just a lot more complex than we could ever imagine. And putting a label on it saying that it's only a wave or it's only a particle, it isn't really accurate. In fact, it turns out that calling particles as only particles actually isn't accurate as well, as you'll learn when we discuss. I don't think we're going to discuss it, but when you talk about modern physics, you'll definitely come up and discuss something called the wave nature of particles, right? Or the de Broglie wavelength. So this is just another picture of what's going on. So you have the light rays coming in these parallel wave fronts, and then as they enter into these openings, they will start to spread outwards in the cone shape. And then as they spread outwards like that, they'll eventually start interacting, and you'll get these areas where the wave fronts are crossing, where you're going to get constructive interference, and then you have these areas where the wave fronts are interacting with the middle, the troughs of the other waves, and that this is where you're going to end up getting destructive interference, and so on, so on. All right. So what we're one thing to note is that we're only going to be considering what's called monochromatic colors, or monochromatic waves, which means just one single color. Mainly because it just makes our lives so much easier to do that, as opposed to dealing with all the different wavelengths, since the amount that it diffracts is going to be different based off the different wavelengths. There will be a time where we do consider other colors being included, but normally we're going to kind of limit it. It's not going to be like pure white light all the time. All right. So, um, yeah, this is what I was talking about. When they interact, they're going to create areas of constructive and destructive interference. The areas where they get constructive interference is where you're going to get a light, bright line, and then areas where you get destructive interference will be a dark line, and it'll end up creating what we call these fringes. Um, and the spacing and the brightness are all based off of the properties of the light compared to the properties of the slits that we're using. Now, there's some geometry that we can do. So, for example, I'm not going to go completely into the derivation, but for the most part, the waves right in the middle of the two slits will end up having being constructive interference, because both these waves are going to be will have started entering into these two slits in phase with each other, and they're going to travel the same distance to that middle point, so the two waves will end up remaining in phase. Uh, Now, if the waves as they go off on an angle, because remember there's like they're spreading outwards, and they're gonna all hit the entire screen. When they hit over here, they'll only be in phase if this wave, which is now going to be traveling a little bit longer than the other wave, is traveling basically an integer wave number. So, for example, if this takes 15 wavelengths to reach this location, this would have to reach something like 16 be like travel 16 wavelengths, or 17, or some integer number of wavelengths. That's what this is saying here. That this distance, if we kind of create a right triangle, this distance has to be an integer wavelength to create another constructive interference or another bright fringe. On the flip side, uh, the area where instead of it being a full wavelength, where this only travels half a wavelength, then we end up getting the destructive interference, where this is now kind of hitting its trough when the other wave is hitting a crest. So we can do something similar to figure out those positions by setting the right triangle and setting this side of the right triangle equal to half a wavelength. Um, so we end up coming up with two equations. You want to be very careful with these, because these equations are going to come up a lot, but sometimes it's what the symbols mean and what it's used for is going to change. But in this case, when we have two slits, constructive interference is going to occur when this equation is satisfied. So D is going to represent the distance between the two slits. Theta is going to represent the angle from the slit to the screen. And then M is the order number, which is just some integer number of 1, 2, whatever, and whatever. And then lambda is the wavelength. So these are all the numbers that you're going to end up using. To clarify, the order number is basically telling us the fringe. So, for example, order number 1 is going to tell us the first fringe from the middle. The second order would be the second fringe from the middle, and so on and so on. Now, destructive interference is going to occur when the equation looks like this. Because remember, we have a half integer wavelength. So it's got to be half a wave, 1.5 waves, 3.5s, whatever, and whatever. Here you'll notice that M changes a little bit. It's no longer 1, 2, 3. It starts at 0 because technically the lowest number that this could be is half. Now, if you don't like that and you want to instead make it so that M is always, starting at 1, then going to 2 and 3, you can actually change this to be M minus a half. It doesn't really matter, but I recommend this only because when we say the first order fringe and talking about constructive interference, the first order bright fringe, that's referring to the first line, and we set m equal to 1. Now, the first order dark fringe is actually the second dark line we see and would result in m being equal to 1. So that's one of the reasons why I kind of keep it like this, is because it's going to make a lot more sense when we say, 0th order dark fringe and first order and whatever. It'll tell you what number gets plugged in for m. Yeah. And another thing is that the pattern that we end up seeing is symmetric on both sides. So even though we've been deriving it for the waves interacting on this side, it also works down here. So the angle for the first order fringe on here is also the angle for the first order fringe on this side. Yeah, so this is kind of what I was saying before. The central fringe, when theta is equal to 0, is normally called the 0th order bright fringe. So just keep, once again, just keep a lot of those terminologies in mind. So this is kind of what the fringes will end up looking like. You end up getting these bright lines and dark lines and so on and so on. And they will start to decrease in intensity, getting darker and darker as you move off. This is just a really good example of what I was talking about before, about the whole first order bright fringe versus first order dark fringe. So here you have your 0th order bright fringe, and then here you have your 0th order dark fringe. So again, this is why m is equal to 0 here, rather than having it start at m equals 1. All right. So one question we can ask, since the intensity decreases as we get further and further from the central fringe, well, one question we can ask ourselves is there a limit to how many fringes we can have? I mean, clearly there will be a point where we won't be able to distinguish a bright fringe anymore and we won't be able to see it, but it may technically still be there. Like, is it something that it will eventually cross 0, or will it just get closer and closer, never actually reaching it? A good example of what I'm referring to is, as you know, things like the electrostatic force and the gravitational force are infinitely far acting forces. No matter where you are in the universe, you will still experience a electromagnetic force and a gravitational force. Even if you don't feel it, it's technically still there. It's non-zero. So does that work here? So what we can do is we can look at this equation, d sine theta equals m lambda. And the thing is, sine theta will always have to be less than 1. That is a strict definition of that trig term. So what that means is if we move the theta over here and we set sine theta equal to 1, because it can never be greater than 1 or even equal to, what that means is that the maximum value for the fringe order is going to be equal to this. So at some point, it will end up being finite. Now, one thing to note is that m has to be a whole number, and it has to be less than this term. If you end up using this equation to figure out what the maximum order that you can find is, and you get that the answer is 2.9, you can't say, oh, m is 3, because I rounded and that's what I got. It has to be the closest whole number that is below what you get. So if you get 2.9 for d over lambda, well then m has to be 2. That is the maximum fringe order for that. All right. Um, Oh, one thing to also note is that the spacing actually isn't uniform. In the beginning, it is somewhat uniform, where the distance between the 0th order and the first order is about the same as the first and the second, and the second and the third. But typically, as you get further away, as that angle becomes more and more noticeable, um, you'll start to see that these fringes will actually separate more and more. One way of kind of realizing that the spacing is uniform in the beginning is by looking at the small angle approximation. If you haven't realized by now, that's kind of one thing that we're always returning back to and using. So kind of keep that in mind. All right. So here's a question that I want you to work on. Use the equation that I just gave you, and pause the video, work on this yourself, and we'll go over it in a second. All right, so we want to know what is the distance between the first order fringe and the second order fringe. So what I need to figure out is where is the position of the first order and where is the position of the second. That's kind of what I need first before I can do anything else. So I'm going to use the equation to solve that for me. So this is the information I have, wanting to make sure that I keep everything in the same units. I use my equation to figure out the position for the first order fringe. And now what I can do, and I do want to point out, is while you can use this most of the time, you want to make sure that you prove it first. So what I did here was I used the sine theta and said, okay, well, when I get this number, I get an extremely small number. Typically, a number like this tells me that I'm going to end up getting a really, really small angle. Since this number is very small compared to 1, what we're going to say is that this theta is a small angle. And I can use the small angle approximation and say that this is about equal to theta, which I can set equal to x over L. Because we get sine is roughly approximately equal to tangent, which is equal to opposite over adjacent. So with this, I can then use the approximation, use this number to figure out what the distance along the screen is, and I get that the first fringe occurs 6 millimeters from the central fringe. I could do the same thing, since theta, using the small angle approximation, is going to end up having a direct relationship with the order number. I know that the second order fringe is going to occur just 2 times away from that at 12 millimeters. So I now have what x1 and x2 are, so the distance between them is going to be 6 millimeters apart. So these first 2 fringes are 6 millimeters apart. All right. Here's another question. So here I do have monochromatic light, but we're only really focusing on 2 different colors. Sorry, not monochromatic, but white light. But I'm only focusing on 2 colors rather than the entire spectrum. So pause the video, work on this stuff, and we'll go over it in a second. All right. So we want to figure out the wavelengths of the violet and red light based off of their location along the screen. So this is the information I have. Now I can basically do the reverse of the small angle approximation. Now I didn't prove it here. I would recommend that you try to prove it yourself. Basically, you just take the 2 times 10 to the negative 3, the 2 millimeters, divide it by the distance between the screen and the double slit, and then you find that this is going to end up being a really small number. So because of that, I can then use the small angle approximation, saying that I simplify sine theta to x over L. So when I do that and I solve for the wavelength, I end up getting 400 nanometers. And when I do it for the red wavelength, I end up getting 700 nanometers, which is pretty much exactly what I expect for violet and red light. All right. Here's the next question. You can pause the video, work on it yourself, and we'll go over it in a second. All right. So we're gonna go and do the same thing that we did before. They want us to find the distance between slits. Um, so we know that the adjacent bright bands are 2 centimeters apart. We know what the wavelength is. We could kind of pretty much do the same thing again. Normally I'd want to prove the small angle approximation, but I just don't want to do it over and over again. But what you can say is, since the distance between bright bands are for lower fringes, lower orders, is 2 centimeters apart, divide that by 4, and we end up getting a very small number. So small angle approximation works once again. Do this, and what we end up getting is a relationship that looks like this, that the position along the screen is equal to the order, fringe order, times lambda L over D. What we can do is say that the difference, like if I took this to be x1 and x2, then the only difference would be the order number. So the difference in its position on the screen is equal to the difference in the order number times lambda L over D. Now again, this only works because of the small angle approximation. If it wasn't for this, if it wasn't for the small angle, this wouldn't work. So this only works because these are lower order fringes. When I do that, I plug my numbers in, and I end up getting that the slits have to be 100 micrometers apart. For part B, we end up illuminating it with a different wavelength, and they tell us that the 5th order minimum is going to occur at the same location as the 4th order minimum for this original wavelength, and they want us to come up with what the new wavelength is going to be. So since this is a minimum, that's destructive interference. So we're going to use this form, the one with the m plus a half. And we know that since they're occurring at the same spot, the sine theta part is going to be the same for both. So what I can do is I set the m plus a half times lambda equal to m plus a half times lambda for the two different wavelengths. Now I put the d in here, but as you'll see, these just cross out because this the distance of this slit is the same as the distance of the slit over here. So I solve for the new wavelength, and what I end up getting when I plug my numbers in, it looks like this. And I ended up getting 389 nanometers. All right. Now, all right. So I'm gonna leave that there for now. We'll continue our discussion on interference and a little bit more about the wave nature in the next video. If you have any questions, please let me know, and I'll talk to you later. Bye.